All right, today we are cracking open a cold case that is, about 4.6 billion years old. Our subject is the sun itself, and the scene of the crime? Its core, a place so incredibly violent and so far away we can never ever hope to visit it. But deep inside, there's a powerful mystery, a hidden engine, and today we're going to see if we can solve it.
So, think about this for a second. How do you investigate a mystery when the room is locked from the inside and the room itself is a literal star? You can't see into it, you definitely can't touch it, you can't get anywhere near it. I mean, this is the incredible challenge that solar physicists are up against. It's the ultimate locked room mystery.
You know, we see the evidence of this engine all the time. Those sunspots that appear on its surface, the huge solar flares that lash out into space. It all follows this strange, repeating 11-year cycle. And it's all being driven by this colossal magnetic engine hidden deep inside. The big question for scientists isn't what it is, but how on earth does it work?
Okay, so first things first, let's survey the scene. We're heading into the sun's locked room, its vast, completely unseeable interior.
The engine we're hunting for is called the solar dynamo. This is the process that creates and cycles the sun's absolutely enormous magnetic fields. You can think of it like the sun's magnetic heartbeat, and our job is to figure out what exactly makes that heartbeat tick.
Now here's what's so fascinating about this case. Scientists all agree the dynamo is real. It exists. The mystery isn't a whodunit, it's a wheredunit. The key to understanding how it all works is figuring out where inside the sun the main action is actually happening.
And just like any good detective story, we need to line up our suspects. In this case, our suspects are three competing scientific models, and each one points a finger at a completely different location for the dynamo. So let's meet the lineup. First, we have two, let's call them the old-timers, the DC99 and CNC04 models. And then we've got the new kid on the block, the ZJ22 model. Each one tells a very different story about what's going on.
And here's where their stories just completely fall apart from each other. The two older models, they claim the engine is buried deep inside the sun in this thin layer called the tachocline. You can just think of it as a boundary layer between the sun's core and its outer layers. But the new model, ZJ22, says, no way. It says the engine is much closer to the surface, churning away in the sun's turbulent convection zone, which is basically just a vast boiling pot of plasma. They can't both be right.
Now, every detective needs a break in the case, right? That one crucial piece of evidence that just blows the whole thing wide open. Well, for solar physicists, that clue is a tiny, telltale wobble in the sun's rotation.
Using a really cool technique called helioseismology, which is basically studying sunquakes to learn about the interior, scientists found this hidden clue. It's an unbelievably subtle, repeating pattern of the sun speeding up and slowing down that just kind of ripples across the surface.
This wobble actually has a name, torsional oscillations. And here is the absolute breakthrough. Scientists believe these oscillations are the physical imprint, get this, the fingerprints left behind by that invisible dynamo. We can't see the engine itself, nope, but now we can see the marks it's leaving on the surface.
So this gives us our whole method of investigation. If each suspect model describes a different dynamo in a different place, it should predict a completely different set of fingerprints, right? So all we have to do is compare their predictions to the real evidence.
Okay, this is it. This is the big confrontation. It is time to take the fingerprints predicted by each of our three suspects and hold them up against the real evidence from the sun.
So to get a match, a model has to get three key characteristics right. First, the migration pattern. The real wobble starts at the mid-latitudes and then splits, with one branch heading to the poles and another to the equator. Second, the alternating bands of speeding up and slowing down. And third, and this is crucial, the amplitude. How strong is the wobble?
And here is the scorecard. Let's break it down. For the migration pattern, the new model, ZJ22, gets a perfect match. Nice. But hang on. It fails on the alternating bands, where one of the old models actually does better. So it looks like no model is perfect until you look at that last row, the amplitude. ZJ22 nails it. The older models, they get it catastrophically wrong. This is our smoking gun.
That amplitude measurement is, without a doubt, the most damning piece of evidence in this entire case. The older models weren't just a little bit off. Their predictions for the strength of the sun's wobble were, and I'm not exaggerating, catastrophically wrong.
Let's put some numbers to this so you can see what I mean. The actual observed acceleration of the sun's wobble is incredibly small, on the order of 10 to the -8 meters per second squared. A
tiny, tiny tremor. So what did the first of our old suspects, the CNCO4 model, predict? A wobble that was 1,000 times stronger than reality. That's not just a miss. That's not even in the same sport.
And it gets even worse. The other older model, DC99, predicted a wobble that was 1,000,000 times stronger than what we actually see, an error of 6 orders of magnitude. It's like predicting a global hurricane and getting a light puff of wind. For these two suspects, the case is officially closed.
So what does this tell us? Well, the paper concludes that because the observed wobble is so weak, the internal magnetic field driving it must also be much weaker than we thought. The older models assumed these monstrously strong fields deep in the tachocline, but this new evidence suggests a more modest field of just a few hundred Gauss closer to the surface is enough to get the job done.
The evidence is in. The alibis are broken. It is time to deliver the verdict on the sun's magnetic dynamo.
The verdict is clear. The ZJ22 model, while not perfect, is by far our lead suspect. Its success strongly suggests the sun's dynamo engine is churning away up in the convection zone, close to the surface. It means the main location of the solar dynamo is probably not in the deep tachocline. And it tells us the sun's internal magnetic fields are powerful, for sure, but not the titans that older theories imagined.
And that is the beauty of this piece of scientific detective work. By carefully measuring an almost imperceptibly small wobble on the surface of our star, we've managed to reach deep inside and learn something absolutely fundamental about its hidden engine room.
But you know, solving one mystery only opens the door to others. If we finally pinpointed the dynamo's neighborhood, what does that tell us about predicting solar storms? And what other deep secrets is our star still waiting to reveal? The investigation, as always, continues.